Hello, welcome back to Paleozoic PCs, where prehistoric computers walk the earth. Today's part 2 of talking about my little video card project. I do apologize for the gap between the videos. It's been a very busy December. But life goes on. So today we're going to talk some more about how the heck this all works. So, as I recall from the end of the last video, we had just left off with me briefly demonstrating this VideoSPI demo that I'd chosen to use as the basis for the source code for my video generators 324 PA Atmel CPU. There's a lot of video generation code written out there written for Arduino. This was just a particularly clean and easy to understand example, so that's why I went with it. But so let's talk briefly again about how NTSC video works. So you probably know the basics. You have your CRT, which is painted by an electron beam that lives in the back. That beam comes out its front. It scans lines across the screen. The lines of electrons, which are steered by big magnets in the back, excite phosphors that are on the glass. So basically all of this is just persistence of vision and persistence of phosphors. There's actually just one little electronic spot that's constantly flying back and forth, painting each line. And then when it gets to the bottom, it flips back up to the top, does it all over again. One trip down is a frame, and it's a little bit different from, you think of like a motion picture where you're on film, where you're given the whole thing at once, and then an entire picture is substituted. This is literally just a tiny little dot that sweeps across the screen at many megahertz, and your eye puts it all together. So each trip across the screen on NTSC is about 63.5 microseconds. On the screen here, I have, if you've looked at this at all, at any sort of video generation like this at all, you've probably seen this exact diagram or one like it. So you can see each trip across the screen is about 63.5 microseconds. And of that, about 11 microseconds of it is assigned to be the horizontal blanking interval. That is where there's a baseline black level, which you have, because remember, there's just a single signal wire in composite video. There's a baseline black level, which is not 0 volts. It's actually about a third of the way, roughly, between 0 volts and the top voltage that's supposed to come out of it, which is like 1.3 volts or something like that. The horizontal pulse is a drop below the black level, where it's held for 4.7 microseconds, and that signals the monitor to fling the electron beam from this side back over to this side. Then after that period, now this gray blob here, this is the color burst. We're not doing color, so we're going to pretend the color burst doesn't exist. So after you get clear of the left margin, then you start actually outputting your video. And you can do that for about 50 microseconds. And then you've got to go back down to black level. You have to stay at the black level for a little while. And then you fire your sync pulse again. Wash and repeat for, if you're doing non-interlaced video, which is kind of a hack on NTSC, but it's what most 70s and 80s computers and and game consoles did. You get 262 lines, and then you have to send the vertical refresh pulse, which involves basically reversing the polarity of the underlying sync signal. So I have, for a quick explanation, I have these two wires running to the oscilloscope probes. The blue wire is the video signal. That's right here. That's the actual dots. And the red signal is the sync signal. As you can see, this period is the horizontal sync signal. This blinking you see right here is during the vertical sync interval. Basically this waveform is reversed. So the this part is the long period, the active video part is down at 0, and then there are these 4.7 intervals get flipped back up to the 0 point to make sure the monitor doesn't lose sync. Now this happens for 3 lines, so basically you get to 262. Then for 3 lines periods, the electron beam will be back in transit back up to the top, and then essentially you start counting at 4 again. Starts painting across. So that's how, that in its most basic sense is how you can do NTSC video. Now if we look over at the screen here, technically, particularly details like the vertical sync period are more complicated than that. If you're doing broadcast quality NTSC, which we are not doing, because with that you have to worry about interlaced, in which case basically every frame is actually 2 fields which are slightly offset from each other. So you have to do 525 lines, but each field is 262 and a half lines, and you have to send these synchronization pulses, which you can see these equalizing pulses. We are not doing that. A major reason that wasn't done by these old computers is, if you're familiar with the Scanline look, let's just go ahead and zoom in here. The good old Scanline look on of old monitors. That gap in the Scanline would be filled by the interlaced frame. Now that would be nice. That there'd be no obvious black lines like this, but each line would only be refreshed at half the speed, which doesn't really matter if you're watching TV. But if you're displaying graphical dots, it will mean it will flicker, because 30 hertz is a little below most people's persistence of vision. So that's why non-interlaced is usually used for NTSC displays. So the bright side, most monitors will accept this much simplified version of NTSC. So you don't have to worry about all this equalizing pulses complication. You can just, as this display is just literally, you get a downbeat, an upbeat, downbeat, upbeat every 63.5 microseconds, and then you pile some video on it, and Bob's your uncle, you have black and white video. So how is this done on a MCU? So if we look at the code for this Arduino Sketch that I'm using, it's pretty simple. The Arduino has the chip, the AVR chips. They have a few hardware timers, and one of the hardware timers is programmed for this cycle. So in the setup area here, that's these confusing lines about TTCR, TIMISC. This is all timer related. And The broad scope of it is it sets up the same timer. So on one interval, which is every 63.5 microseconds, it will drop down. It'll drop the value of a pin from high to low. And then after 4.7 milliseconds, it'll pop back up and send that back to high. And it will also fire an interrupt each time. During the logo and interrupt, all it actually does basically is when it goes down, it actually puts the CPU to sleep briefly. And the reason it does that is long and complicated, and I won't get too deep into it, but basically it ensures that all of the lines, when it wakes up, start at exactly the same number of microseconds since the beginning. Then the second, when it pops back up, it runs, you see it runs line handler, which is actually a pointer to a function, which either outputs blank lines, outputs the vertical sync signal, or outputs the video, and then increments, and then when it gets to, starts from 0, then it gets to 262 lines. That's when it fires off the vertical syncs, resets the counter, waits 3, starts over. You get the idea. Again, I would highly recommend this piece of code as a good introduction to doing video with Arduino. Okay, so now I've got the oscilloscope rewired, so we're getting the same feeds as before. We've got, you can see the sync pulses just exactly like from the Arduino project, and you can see the video takes roughly the same section of the total space available. Now, one thing you may have noticed that my board is capable of is multiple pixel clocks. See, this is a ridiculously low pixel clock. This is a 4 megahertz pixel clock, and because my original target was for like TRS-80 or S100 video, I decided to go, instead of using a 16 megahertz crystal to drive the CPU and as the maximum pixel clock, I've actually gone with a 12 megahertz crystal. Now the 40 column mode, so this is a 32 column mode, this is a 6 megahertz pixel clock. There's now a good 40 column mode, which we didn't have before. This is the same 8 megahertz as the other project. This is 12 megahertz, and then you saw the ridiculous 4 megahertz mode right there. That's a VIC-20 for you right there. How do we do that? Well, it's not CPU code. I just wanted to bring it up. That you notice if it cycles, you'll see slight differences very slight differences in the timing. Or the oscilloscope will bounce around a little bit. But it's actually the exact same synchronization code loop runs all the time. It's just the dot clock and the synchronization code that tells it to spit out the dots that changes for each pixel clock. So anyway, that aside, let's talk about how we actually get this how we get to do video with external memory instead of internal memory. So I think first it might be instructive to look at how a real 70s computer would have done it. So on the screen here is a schematic for a Commodore PET. The original, well, it's actually the second version of the PET that didn't use a CRTC. It did everything with discrete technology. So up here in the upper right corner is the actual video output. We've followed the chain back There's some stuff we can mostly ignore. And we get down to a shift register. Now, a shift register is a simple device. Here's a most common example of the sort of thing involved here. This is a parallel load serial out shift register. It has basically 8 little memory locations, which can be written with by applying a parallel byte to the chip, and then a pin is toggled, and then that loads the contents of these flip-flops, these memory cells, and then there's a clock which is applied to it, and on every tick of the clock the device takes 1 bit, it shoves it out of the output right here, and then everything plays musical chairs, it moves over. So it goes tick, tick, tick. And with each tick, it will also read a new bit off of the serial input. So the main use for that would be if you wanted to, say, do a 16-bit load. You could take 2 of these, you could chain them together, you'd put the output from one into the input of the other, whatever. But generally you would just tie the serial input for, an 8-bit application. It would just be tied to ground, so it's just 0 all the time. So basically what this means is you only need to read memory once for every 8 pixels that goes up on the screen. And that's really important if you're talking about 1970s technology, because memory of that time, again, like a 40-column screen requires a dot clock of around 8 megahertz. Memory from the 1970s could never run at 8 megahertz if you had to read it for every pixel you shoved out. So this allows you to do a 40-column screen with only 1 megahertz memory. So if we get back to the PET, so you got the shift register, that's connected to a character ROM. It doesn't get it directly from memory because the PET was not capable of actually bitmap graphics. It could only do characters. But you can still imagine that it's a bitmap that's stored in the character ROM. So the contents that are presented out the character ROM are drawn from memory. How they get there is, here's the memory chips. There's 2 of them. Each one is 4 bits wide, so it's an 8-bit memory. So during the video cycle, this bus right here is fed with an address which is calculated by the video address circuitry. The video address circuitry is the thing that for every cell on the screen, it keeps track of what is the memory location associated with that. So that's this circuitry over here that does that counting, but we don't need to worry about it. We just know we get an address, it's read in here. There's a pulse that tells the chips to output the memory at that location, and that is fed into a latch. The reason it's fed into a latch instead of just straight into the character ROM is because the memory of that era was barely fast enough to be able to share between the CPU and the video system. So by feeding this into the latch, it allows the video system to tie this up for less time. Basically, the latch is very fast, so when it gets stuck in the latch, it can then give the video memory back over to the CPU as soon as possible, because the character ROM is going to be pretty slow. Then the character ROM's it's going to lag behind a little bit. So it goes in the latch. When the character is ready to be output, it immediately outputs the same value that it latched out here, and then that tells the character to find the row of dots associated with that character. So if it's a letter A in here, that's on a PET, that's ASCII code, PETSCII code 1. So you'd have 1. Now you notice if you were actually looking at this, that we're not starting at A0 for the address lines here. We're starting at A3. The first three are actually connected to the circuitry over here. That's because this is character rows. So there's this counter over here that keeps track of, each character is 8 lines tall. So this counter goes 0, 1, 2, 3, 4, 5, 6, 7 over and over again. And so the 8 lines that make up each character are stored sequentially. So on each line, as this will be updated on each line, the correct character will be chosen in this, and this line that says graphic with A10, this character ROM actually has 2 sets of pictures in it, 2 character sets that will switch. Now you may notice again, if you're sharp-eyed, that only 7 data lines went to this. The reason for that is because on the PET there are 256 possible characters, but there are only 128, because you got an 8-bit byte. There are only 128 glyphs in each font. When the high bit is set, then this circuitry that we kind of ignored up here will actually invert the output, so you get reverse video. You get the same characters as the first 128, but they're in reverse video. But anyway, that's how a real thing does it. And the special sauce is basically the timing and the address generator. So on a real machine, you can see it's a few counters. This latch is used because, basically it has to count from 0 to 39, 1 through 40, 8 times over and over again. Add an offset to it because each line is 40 characters. It then has to do each line 40 times, so it has to remember what line it's on. That's what the latch is for. And then when it's done with 8 lines, then another counter pops it up through memory, so it does the next 40 characters 8 times. Like in the first video, I mentioned that 64 column video was very common on these ancient computers. In part, it was because if you make your video a power of 2 wide, then you don't actually need this latch anymore, because it's 64 is easy. You can just let a 6-bit counter run over and over again. So that's how a real machine does it. So that's exactly what we're doing on our hardware, essentially. All the lines coming out of this side of the MCU, they're mostly blue, going into this is still just a ROM chip at this point. These are the address lines. If we look at the code that I wrote, for each line, and we'll look at the high-res line, I think, because it's the simplest. For each line, all we do, we have to load some registers and stuff first, but basically the first thing we do is we just output the address of the character at the start of the line. Then and from that point, the ROM chip will just automatically spit the correct value out on its data lines, which you see here go to a shift register. We're going directly to the shift register because we don't need a latch right now. There's no contention over memory right now, so we can just hold that value. And then a load signal is generated for the shift register, so it latches that in the shift register, and then the shift register is clocked to the pixel clock and spits out the lines. So if you look at the loop, this is the highest res line, which only gives it 8 clocks per cycle. So at the start of the line, we start the shift register shifting. Then we output the dot line. That's one instruction. Second instruction. We're doing this knobs here because So we lead into the actual loop. On the loop, we increment we basically, it takes 2 instructions to a 16-bit number. So from our starting address for the line, we add the increment, which is usually just 1 for the line. Then we update it. And then you might notice we just do a NOP, and then we see the DEC and the BRNE. That's the loop. So we have like the total number of characters per line we're going to output. Each one of these instructions is just 1 clock cycle. So at 12 megahertz, you've got 1 clock, 2 clock, 3 clock, 4 clock, 5 clocks, 6, 7, 8 clocks. You might notice that we did not actually send anything to the shift register to tell it to shift. So how did we do that? So that's where we get into programmable logic.